Start in a minute. Okay, let's start. Welcome to the midterm review session for cryptography. This will be about 2 hours. If you have doubts at any point, just stop me. We have a bunch of stuff to cover, and there will be a bunch of questions in the middle that I'll give you a few minutes to solve, and then no, this is yours.
Previous class.
Was that supposed to read stuff? I wasn't told that I was supposed to print them. So, I mean, the questions will be on the screen, so we can stop there and solve. This is, no.
Oh, this is previous class. Someone say. Oh.
Okay, let's start. Anyone has any questions before we start? No. So cryptography, why do we study cryptography? Why is it interesting? How does it help us? The answer is secure communication. And today, if you ask a cryptographer, they might give you a different answer, but in this course, we cover a more basic version of cryptography where all we want to do is we want to communicate securely with people. And there are 3 parts to secure communication. The first one is that you want to make sure that whatever you are communicating stays hidden from any adversary who might be listening on the network, which is known as confidentiality. The second one is integrity. You want to make sure that if I'm sending a message to you, no one can tamper with the message. If they try to tamper, the recipient will be able to detect tampering. Okay, this is integrity. And then authenticity means that you can know who the message is coming from. And people cannot masquerade as someone else. If you get a message, you know where the message came from. So these are 3 important properties that we want pretty much any system that communicates over the web to have, right? That was supposed to be some animations anyways. So how do we measure confidentiality? Oh, yeah.
The Zoom is running?
Yeah, so it's running. If someone can, I think the audio is on, so if anyone on Zoom has question, you can just start speaking, that should be fine. Okay. Okay, so one way to measure confidentiality is that we define this game called INDCPA. What it stands for is indistinguishability against chosen plain text attack. And what this means is it's a very simple game. All this game is saying that, let's say there's 2 parties, there's Alice and there's Eve. Eve is sort of our, here is sort of our adversary here, and Alice is someone who actually wants to communicate. And what we say in this game is that we're going to give Eve a lot of power because we want to construct a strong scheme. So we will let Eve choose 2 messages of her choice. Let's say them M0 and M1. Alice will pick one of those messages at random, and she will encrypt that message and send the ciphertext back to Eve. If Eve can guess correctly which of those 2 messages was encrypted by Alice, then Eve wins the game. Otherwise, she loses the game. Okay, so what this sort of tells you is that even if you know what message is encrypted, looking at the ciphertext, you wouldn't be able to tell which message went where. Okay, so it's sort of a very strong confidentiality guarantee that you get from this scheme. Now you might ask, okay, what happens if Eve, so Eve can actually send any messages that she likes and can get ciphertext back. And yeah, and can someone tell me why half probability is always possible in this way? Like for Eve to win the game, she has to do considerably better than. Who wants to quickly answer this question? Yeah.
I mean, it's just random paths. If you're going to choose, probably answer around.
Yeah, it's a bit which was sampled by Alice. That's the only unknown, and it was sampled uniformly. For some reason, I don't know. Okay, cool. It just started beeping by itself.
Yeah.
That is very annoying, yeah. We don't want to turn it off.
Okay, fair enough.
Okay, so that's the game. Now, in this game, there's something, let's go back to the game actually, and let's look a bit closer in the game. So what's happening is that actually Eve can even ask for these two messages, for example, to be something that she already knows or has an encryption for. Or she can ask for multiple encryptions of these messages. Okay, which means that if the scheme was deterministic, you would get the same ciphertext for each plain text. Then if she has this information, she first, so let's say before this game starts, before she picks her two M0 and M1, she asks for encryption of M0 and then plays the game with the same M0 and M1. If this was a deterministic scheme, then the two ciphertexts, she would see that the new ciphertext that she got, if Alice chooses M0, would be the same as the ciphertext she already has. Which means that deterministic schemes don't stand a chance against this game. You need a scheme. Yeah.
Session recorded.
Yeah, I think so. Yeah, I did hear that it's being recorded when we started it. I think at the bottom.
Yeah, it's recording.
Okay. Okay. Cool.
Yeah.
Oops.
I clicked through.
It's fine.
Okay.
Yeah. So determinism in encryption schemes means that yeah, if you get the same ciphertext whenever you encrypt the same plaintext, and in this case, your scheme cannot satisfy this in CPS security. In CPS security, by the way, means that when the chance of Eve winning the game is almost half, it is not much farther than half. It can be just a bit, slightly bit better than half, but it has to be still around that same ballpark. So that is the general idea. Okay, so that's good. No, this will work here. Now let's look at the XOR function because it's going to be useful for us going forward. XOR function is just you're doing a computation modulo 2. So whenever you add something with it, it becomes a 0. Whenever you if we want to talk about bits, it can be if you have differing bits, the XOR would be 1. If you have the same bit, the XOR would be 0. If you XOR something with itself, you get a 0. And if you XOR 0 with anything, you get the same. I'm guessing this is pretty standard stuff. Everyone's already played around quite a bit with the XOR function. And okay, so one-time pad. One-time pad is the most is actually the most secure encryption scheme that you can construct, but it also has very big limitations. So the idea with a one-time pad is that let me sample a random string, completely random string, and let me mask my message with that completely random string. My message, and let's call that string the key K. And what you get after this XOR operation is something that looks completely random. There is no information about the message in that string itself. Because if I just give you K XOR M, and you look at this this quantity, I can go back, and you don't know what K is. I can go back and change my K, and that will change the message. I can make the message go to any possible locations just by changing my key, which means that the message that you see has literally no information. It is contingent on the fact as to what key I hold in my pocket. That makes sense? So it is the most secure encryption scheme you can construct. And anyone wants to tell me what the problem with this encryption scheme is? Like, why are we not using it then?
Us and Bob would both have to know what the key is for every single message that they
Exactly.
share between each other.
Yes, and there's one more thing,
You're never allowed to reuse,
which means
which means you have to have like infinite randomness.
exactly it. Basically, you're just pushing the ball down because your task was that you wanted to communicate this message and security to the other party. Now you want to communicate this key, which is exactly the same size as your message and cannot even be reused. So that is an issue why one-time pad is not used directly, but as we will see, in AES and its mode of operations, you do use something like a one-time pad, but where the randomness would be pseudo-random, it wouldn't be a completely random string. Okay. Anyone has any questions about one-time pad? I'm guessing this is all pretty standard. Also, if we're going fast over a section, just let me know. I'm not sure how detailed these things were in the lectures. Okay, and this is good. Also, let me know if you want to cover up the section, Margaret.
I think I can cover starting from questions.
Okay. So what is the problem with one-time patch? Some of you already answered some of these questions. You have to generate this random key for a message. It is expensive. Now both need to, both Alice and Bob, if they want to communicate, they need to share this key. And yeah. So one way where you can use it is, let's say you bootstrap a system. Let's say I just started a system for the first time. I send all their recipients very long keys that they can use for the lifetime of the system. And now I can just, now I'm no longer worried about an attacker now after I've distributed these keys getting into my system, because by this time these one-time pairs have already been distributed. So it's sort of a very made up scenario, which is why it is quite limited. Okay, so let's do a block cipher now. So what a block cipher does is it takes a block, it encrypts it, and gives you the ciphertext. Take the ciphertext, you put it in the decryption algorithm, and it decrypts that block. So you have this encryption algorithm, decryption algorithm. Encryption algorithm takes a plain text n bits, which is a block size is n, a key with k bits, and it gives you a ciphertext with the same bits as the number of as the plain text. And then you put this ciphertext into the decryption algorithm, you use the same key, and you get the plain text back. And since someone wants to answer this question as to why we typically say that these encryption and decryption blocks are just permutations. They're taking something, for example, let's say if n was 2, and let's say with some key we were getting this mapping, so 0, would be encrypted to 0, 1, 0, 1 would be encrypted to 0, 0, and so on. Why is this? Why does it have to be a permutation? Why can it not be something else?
Maybe because you're using.
Exactly, yeah. So if you are, let's say here, if both 0, 0 and 0, 1 were encrypted to 0, 0, if you get 0, 0, you don't know which one to decrypt to. So it has to be a one-to-one both ways, which is why it is a permutation. So all this is doing is, as you change the key, this permutation would change, but it would still be a permutation. And that is the part that's hidden from an adversary. The adversary does know what E and D are. It knows exactly what they are. It just doesn't know which key they are instantiated with for this communication, which means that it does not know which of the several permutations are being used. Now, let me ask you another question. Let's say K was much smaller than N. Can we cover all possible permutations with the number of possible keys we have? You cannot, right? You can have a much larger plain text, much larger ciphertext, and the number of keys you have might not allow for all permutations. But that is okay, because as long as the number of, as long as the, say, the entropy, which is the uncertainty as to how many possible keys there are, as long as that set is really large, we are good. Because even if I know that not all plain text ciphertext combinations are possible, right? I can enumerate over all keys, let's say, and I find out that these combinations just are not possible. That is still fine as long as this just that enumeration was very expensive for me to do. Okay. So, okay, so the block cipher, we obviously need correctness. We want that if you encrypt something, you decrypt the same thing back, you get your message. Efficiency, we want encryption and decryption to be fast. And yeah, for security, like we said, it behaves like a random permutation without the knowledge of the key. Now, the question for you, is this an NCPA secure scheme or not? Someone in the back, if anyone in the back wants to answer this question. If I just give you a block cipher, does this satisfy NCPA? See a lot of heads nodding as no, but does someone want to answer this in the back? Okay, yeah,
I guess it's deterministic.
exactly. It is deterministic right now. If I give you the same, since the key is fixed, if I encrypt the same plain text twice, you will get the same ciphertext. So it does not satisfy NCPA security. And that is what we're going to fix now. So yeah, block ciphers by themselves don't satisfy NCPA. Another issue is that since they operate on blocks, what if my message is smaller than a block? I'll need to do something else. I cannot, with the way I presented it right now, it doesn't work. So it needs fixed sizes. And the solution will be to use these mode of operations. Okay. So the first one, and probably the most primitive mode of operation, is ECB. It stands for electronic closed book. The idea is that if you have your message and it is divide your message in number of blocks, right? Let's say you have a large message larger than the block size of the cipher, and you put each block through the block cipher. And whatever ciphertext you get, you just concatenate it together, and that's it. So this is probably the most standard way. If I told you that, hey, let me give you a block cipher, but my message is actually 2 blocks, what would you do? You would say like, hey, let's chunk the message into 2, and let's put each of them through the block cipher. Okay, so is this NCPA secure?
Yeah. Because it's deterministic and you use the same plain text and the same ciphertext and combine it together.
So let's say my message was, hello, hello. I'm a person who just says that twice. You know that you see the same ciphertext at the beginning of my message. Yeah. Okay. So this is good. Now this is where we start introducing these IVs or nonces. So nonce is a number used only once. And that is a way for us to inject some randomness into these ciphers. Okay. So they're just a bunch of random bits, which have to be unique, so you don't want to reuse them, and they are public. You don't need to hide them. You can just actually send it along with your message to the other party, because the other party might not know what nonce you use, so they won't be able to decrypt unless they know the nonce. Okay. Any questions? Yeah.
If the IV is public, how are they not able to just use the IV to decrypt it? Like use the IV and like the deterministic method to decrypt it?
Yeah, so by IV's public means that you have to send it along with your message. That's what I mean by public, and you don't have to encrypt it. You could also decide, if I were talking to you, we could also decide that, hey, tomorrow I'll send you a message and the IV would be this. And then I don't need to send it to you. Does that answer your question? Like,
Wait, so like if the IV is public, everybody, the hacker knows what it is.
yes.
So if the hacker knows what the IV is and the method of decrypting is deterministic, why can't they use both those information, just the same information that the person decoding it has to decode the message?
They don't have the key. They know the IV, they know the ciphertext.
Uh-huh.
They don't have the key. So let's go back. The reason this did not satisfy, wait, this is next. Yeah, the way this is deterministic, or like, so right now, let's answer this question. what can an attacker learn about a message under ECB? They cannot decrypt your message directly because it's encrypted with a key. But what they can do is they can know, for example, which blocks are the same plain text. So like I said, if I encrypt hello, hello, they would know that, hey, these are the same messages underneath. So it's sort of this partial leakage, and there's many research papers that show that since language and like you can have other information about when people talk, what they talk about, you can use that to actually learn basically everything. I think there's this this very famous quote. There are a lot of talks in cryptography that this is their first slide, which says that this director of NSA back in the day, and he said that we kill people with just this information, like just metadata about encryption. So you can learn quite a bit of information by just knowing even if two messages are the same. You don't know the message, but you know that they are the same. So we want to solve that problem, and that is why we are introducing these IDs. And the simple idea is that, let's say with my plain text, I added just a counter, let's say. So the first time I encrypt hello, it would look different than the second time I encrypt hello, right? So that is sort of the general idea. Okay. So this is our first mode where we actually use an IB. It's called CBC, cipher block chaining. And the idea is like just what I mentioned. You take your plain text and you XOR it with the IB. This becomes your sort of new plain text, and you just pass it on to the cipher blocks. Now, since we don't want to have IVs as long as our plain text, because then this is the same one-time pad problem. So what we do is we know that the ciphertext is going to look random. So why don't we use that ciphertext as the sort of ID for the next plain text? That's how you chain it together. And as you can see, there's like if I were to choose my ID randomly, like uniformly, then this is actually a one-time pad, right? Because IV is the same size as my plain text, I XOR them together, this is a one-time pad. What comes out, let's say the ciphertext looks pseudo-random. It looks very close to random. Then what's going on in each of these XORs are sort of these pseudo-random one-time pads. So you can see how, but actually we don't even care about, we don't want that strong security because IVs don't have to be random. They just have to be numbers that don't repeat, right? But just to connect this idea to one-time pad, this is how it works. Any questions? Okay. Now, how does decryption work? So you just flip it. Take your ciphertext, or if we go back, the last thing was encryption. So you first decrypt, XOR the previous ciphertext, get the plain text back. So ciphertext, decrypt, XOR the previous ciphertext, get the plain text back. And you can do this all the way. Right? And the nice thing is that you can someone tell me if you can do this in parallel or not? Like, can I decrypt, can I just pick a block and just decrypt that without decrypting anything else?
Yeah.
Yes. Yeah, because all I need to decrypt a block is that block itself to feed it into the decryption algorithm and take the previous ciphertext, which I already have, and I will get the plain text back. So that's a desirable property of this mode of operating. And I'm guessing it's clear that this does satisfy MCPA.
How do you know the size of each block? Is that just the sign?
The size of each block is determined by the encryption scheme itself, so it's a parameter of the scheme. And we will come to the problem as to when your message, let's say, doesn't fully occupy the block. What you do? We'll use padding of a certain kind. Okay, so next is a cipher feedback mode. It is slightly different than the previous scheme. You basically push your XOR operation to after you encrypt. Okay. So you take your initialization vector, you encrypt your initialization vector, and you XOR your plain text into the output of that. And then you feed that onto the next block and so on. So like there's many variations of this. You'll see like in these mode of operations, there's multiple ways you can achieve a similar. So that's the scheme. And yeah, the decryption is straightforward, so I'll just move forward. Now let's come to the last mode, which is counter mode, which is probably the most widely used mode, just because it's quite easy to use and it has a few interesting properties. So what you do is you choose a random nonce to start with, let's say your ID, and then your ID for each of the consecutive blocks will be your nonce plus a counter which you move up. Okay, so as long as you know the nonce, you can directly jump to a certain block and just encrypt that. So in all the previous schemes, in the previous modes, to encrypt a block, if I couldn't have encrypted the last block without encrypting everything else. I could decrypt individual blocks, but I could not encrypt them separately because I was chaining feedback forward. In counter mode, we fixed that problem. You can just go to any block using counter and just encrypt them. Any questions?
So this is ING secure, right? CPU secure?
Yes.
Oh,
Because you have a nonce and the counter ensures that the combined nonce, which is nonce plus the counter, never repeats. So that's this mode. Yeah, decryption is also pretty straightforward. Now let's do some practice problems. We move that away from the question statement. So,
Which one?
move it a little, yeah, yes. Thank you. So how much time are we supposed to give for questions?
I like to give like 2 minutes per subpart.
Okay.
The thing is, like, you should just aim to end this section around 6, and then we'll do the second half from 6 to 7.
And you, by the section, you mean
But
till the max start?
yeah,
Okay, yeah. Yeah, I think that should be, we're on time. Actually, ahead of time, I would say.
yeah.
Okay, so let's take a few minutes to do this. If people have already done this, or then you can just let me know and we can move to the next one. let's discuss this question then. So as you can see, this scheme is like a version of what we discussed. And anyone wants to answer the question? Someone who hasn't answered so far. Oh, yeah.
Would it be B? Because the doesn't, like, if you know the IV, then it would still be deterministic.
Just click.
I can answer these.
Yeah, I'm the same thing.
Oh, I see.
So. Yeah, you move it. Move it. I can-
Yes.
Yeah, so the ID is the same for every block. And let's say it was randomly generated. Since there's no chaining happening, right? You're encrypting something the same ID, you're going to have. Right?
It's like the hello thing.
Yes, exactly. Yeah. Okay, I mean, I think when you click on something, this
Right.
Yeah.
Yeah. Okay.
so
Oops. So it's over here.
knowing that AID and ID XOR with all the messages.
Do you want to answer the chat question actually? So why can't the IVs be the size of the plain text?
Oh, you mean like the entire plain text?
Because it's
already
broken
the-
up into blocks.
Yeah, because the message is broken into blocks and the ID is the size of one block. Right?
Should be.
Yeah. I don't know if it answered your question, Anand, but yeah, okay.
Okay.
Okay, anyone wants to answer this?
The H.
Yes.
Because it's like doing just pretty much just one block cipher without all the chaining.
Exactly.
Yeah.
Yeah, and anything beyond that would be losing information because you basically merged M1 and M2 together, just becomes M prime, and there's just no way for you to know whether it was M prime or it was actually M1 XOR M2. So yeah. Wait, I think let's do the other one as well because if I click next, we'll get the answer for you. So what you said was about correctness, right? Like, can you decrypt something that was correctly encrypted? The next question is asking, if someone looks at this, what can they deduce?
Is it D because it's merged with different messages, right?
Yes. So also what we basically answered also that it's anyways, you cannot encrypt anything beyond a message, right? And with a message, you already have an IV which works well. You don't need the chaining, and there can be no sort of repetitions in one chain of message, because you just XOR it together. It's basically an unusable scheme, but it is secure. Right?
Because it
You look a bit
creates.
confused. No questions?
No.
Okay, right. Yeah, let's move.
There's a explanation as well.
So we can go over the explanation. So if the message is exactly one block, we treat it like AES TCB under one block. And which is fine. If you have more than a block, we lose information because we are XORing things, messages together. So it only works with one block. Yeah, for the next one also, like we discussed, there's nothing that leaks because there's just one block. Okay, so the next one. This one, let's go step by step. So let me ask just the first question. If you use reuse IVs, does it ever leak the secret key solved? It's like most people are saying no, which is good. Yeah, you don't leak secret key like that. What about partial information about plain text? If you reuse IVs? Yeah. And the reason for that is that the hello example could be an example that you can use. The third one is a bit tricky. Does it actually leak the exact length of messages? So let's say the output of the E block, encrypt block, is a fixed size block. Okay, that much we know. The message can be something which is maybe a bit smaller than a block size, let's say. So what you do in that case is you XOR them together and you just remove the bits of the encrypt block which were not important for you. So for the last block, yeah, you do that for the last block because yeah. So in this case, the exact length of messages will be leaked because you're XORing the message outside of what you get from the encryption algorithm. So like it says here, since the encrypt algorithm is only feeded the left. So I think I can explain it better this way. Let's say your you had two blocks. You had a block C0, which is just the IV, and you had a block C1. And let's say your message was smaller than the block size. What would you do? You would first encrypt the IV. So to compute C1, you would encrypt the IV, and you would take that result, XOR that with your message. Since your message is smaller than the output of the encrypt is smaller than block size, you would drop the last two bits of the block size. And you will still be able to decrypt, because to decrypt, you'll take the previous block, which is IV, which you still were given info. You're only doing this dropping the last two bits for the last block, and to decrypt the last block, you don't need the last block size. You don't need the full last block size. Yeah, so exact length of messages isn't. I would honestly say that I don't like this part because the question never specifies what you have to do with the last few blocks, with the remaining part, or like with the part that's left after the message in the block. It doesn't say you have to drop it. It's just that after looking at this, you realize that, yeah, they're doing that. So, yeah.
Do you have the same issue with regular CFA, or is it only when you're reusing?
So this issue will always happen because this is an issue of how you're encrypting the last block. So to encrypt the last block, you're taking the previous block, you're encrypting the previous block and XORing your message to the last block. Which means that if I have to decrypt my last block, I decrypt the encryption of my previous block and XOR my message out of that. Which means that I never had to feed the last block into the decryption algorithm itself. And decryption algorithm is what requires a block size input to give you a block size output, which allows you to do something like this. So like if you put in E outside of that, outside of the MI, then you would not leak the exact length of messages because then your MI XOR whatever would be fed into another encrypt block, which means that you cannot truncate the part last few of it. You have to send it inside the hole. So, which I think is the next question, part of it. The first part, can the secret key be learned by anyone? Easiest one to answer. Is, yeah. So what about the second? Anyone wants to answer why though? Anyone in the back, except for you? Just letting other people also the chance to speak. And what is unique about this scheme? There's this unique aspect that they're sort of constructing their own counter mode, to say. And how do you think that helps?
Like no longer deterministic?
Yes. Yes. The output would be no longer like the input to the block cipher would no longer be the same. Yes, it is still deterministic, right? Because even for an adversary, they know that you put 1 to the first message, 2 to the second message, 3 to the third message, but at least there's no repetitions, right? And that is what basically it remedies the reused IV problem.
It's saying like, even if it was like 1 hello, 2 hello, 3 hello, all the way to all of them would still be decrypted as something different, and thus,
Encrypted is something.
thus you wouldn't be able to tell the difference.
Yes. Because the bit string of the message is different now. It's never repeated. And this one, the exact length of messages. Or you think she cannot remember the exact length of messages? It's a trick question. So the difference from the previous one is that in this case, to encrypt C1, with these questions, you can always just try a first few blocks. It's always just easy to instantiate these things. C0 is the IV itself. So to compute C1, you're taking the message, you're XORing it with the IV, and then you're encrypting it. And the input to an encrypt block is has to be the full block size. And the output also comes out to be a full block size. Which means that you, in this case, to do this, you will have to pad your message. There's no other way. If your message is smaller than a block size, you will have to pad it to the block size. Otherwise, you wouldn't be able to do this operation, right? Which means that in this case, you will be sort of hiding your exact message length because you will be padding it. There's just no other way to do it. In the previous one, you didn't have to do that.
So you said the padding is needed because block size is greater than the message.
Yes, whenever it's greater than the message size, you will have to do some padding here. What, yeah,
How does this compare to counter mode? Counter mode would be like a non-denied counters. How is this?
they are trying to do something similar. So, okay, let's see. So they're using the IV, which is another name for nonce, and they are injecting this counter into the message itself. If we quickly go back to counter mode, it looks pretty similar to, you had your nonce, which would be the same each time, but you would have this counter which would go up. And in that case, you're putting the counter into the plain text itself. In this case, you would put it into the nonce, encrypt it, and then XOR it with the plain text. Oh, yeah. It's just another spin added. But I think one thing, which is that there's no chaining also. So I think it is pretty much the same, yeah. It is trying to emulate counter mode just a little bit. Okay, so in this case, basically nothing is leaked. It'll go down, go up. Yeah.
Alright, so we're going to start on hashes, max, and difficulty. Yeah, let's jump into it. So the first thing we'll cover is hashes. And what is a hash? It's essentially if we have a message of arbitrary length, a hash of that message is a fixed length n-bit hash, where we can have some arbitrary length message, and we will know exactly how long the hash is. Important properties are that it looks random. So even if your messages are similar, the hashes computed of those two messages will be wildly different. It'll be fast. The hash function itself is really fast. It's one way, so that given the hash of a function, given the hash of a message, it's really, really hard to find the original message. And it's collision resistant. So that given two hashes, or given two messages, it's really hard to find matching. It's really hard to find two messages that have the same hash. Any questions so far? All right, so let's take an example. For this example, assume that the hash of M cannot be replaced and tampered with. So we know that Alice wants to send a message to Bob. And let's say that Alice sends the hash of the message as well. Well, if the message is tampered with, Bob can just calculate the hash of the message and know that, hey, someone messed with the message. This isn't what Alice sent. So back to the question, can hashes provide integrity? The answer is not alone, because hashes are unkeyed. Remember that hashes are a public function, so that anyone can compute the hash of any plain text. So the solution to this is max. So what is a message authentication code? Well, the idea is that you have a message and you want for your recipient to be sure that the message came from you and was not tampered with, for example, by some insecure channel. To start, both people have the same key. This is very important because we need this key to both encode and decode or check the MAC. So we're going to throw the key and the message into the MAC function. We can pass it through the insecure channel along with the message. So we have both the message and the tag through the insecure channel. And then once Bob gets the tag, he can use the same key and he will verify that the tag matches the message. Questions so far? Okay. So For the specifics, we have a key generation function that generates a key K. And a MAC function that takes some key in a message and generates a tag. The inputs are a secret key and an arbitrary length message, but the output is a fixed length tag on the message. So what are the properties of MACs? Well, we want the MAC to be deterministic. For example, if we pass in the same message and the same key over and over, we expect that the same MAC will be computed. This is how we can ensure that the message wasn't tampered with, because we should know exactly what to expect from the MAC function. The efficiency, computing MAC should be efficient. It shouldn't take forever to compute. And security. For EUCPA, this essentially means that an attacker cannot create a valid tag on a message without a key. Why is this important? Well, if you can forge the corresponding MAC for a message, then you can just swap out both the original MAC and the original message, and the recipient won't be able to tell that you swapped out either of them. So first question, does MACs provide confidentiality? I'm seeing no's. Can anyone tell me why? Well, yeah, the answer is no, but the reason why is that they're deterministic. They're meant to be deterministic, and this is a property that we want. So it's not necessarily something bad that they're not confidential. We'll just have to use some other method to ensure that they're confidential. Or the message is confidential. So for authenticated encryption, we have two methods. We have MAC then encrypt, and we have encrypt then MAC. Which is better. Both of them are technically IND CPA secure and MU-CPA secure, but MAC then encrypt requires decryption before tag verification. The lesson is to always use encrypt then MAC, because if you MAC then encrypt, then you will be forced to essentially decrypt some message of unknown origin and some message that you haven't verified on your own machine, and this can be vulnerable to side channel attacks and whatnot. For more information, there is this link here on the slides, posted on the ed. It'll lead to, I think, the Lucky 13 attack, which is just an example of a side channel attack. So let's go to the first practice problem.
There's a question.
Oh,
Over there.
yep.
So what's the purpose of hashing in the first place? Like, does it work together with that? Or
Yeah, so the idea is that the hash originally did not have this key right here, right? Which means that anyone can compute the hash given a message. But if we combine the hash function with a key, we're creating a message authentication code, which is essentially the same thing as a hash, but the distinction is only people with this key can calculate the message authentication. What else? Yeah.
And here, Alice and Bob need to both have the key.
Yeah.
On doing that. How does this not like cause problems like how we were talking about before? Like how are we making sure like this key can be reused, I'm assuming.
Yeah.
In this case, yeah. So it's just something that kind of Alice and Bob just have to securely share with each other and stuff.
Yeah.
Okay.
So essentially, in terms of like sharing information, when you don't already have shared keys, that's when you would turn to stuff like Diffie-Hellman or RSA, where you'd have like someone's you'd be encrypting a message through someone's public key, and then the recipient would decrypt it with their private key. Yeah.
So when you combine the hash and the MAC, then you get something like HMAC, right?
Yeah.
So that is secure itself when you combine two together?
Yeah. So HMAC is just a implementation of a MAC. The MAC is just the general idea, but the MAC itself guarantees authenticity. Yeah. What else? All right, let's move on to the problem then. I'll give you guys a couple minutes to look at the problem and think about it, and then we'll come back.
Yeah. Small section. Next one, big. So you're doing all the end, right?
You want to swap it?
Up to you.
I can just take care of it.
Yeah.
Do we think we have 2.1 ready, or we need more time? Thumbs up if you need more time. Okay, I'll give you guys a few more seconds.
Also, because you need the key. Yeah. Look. So there's a clarification. And maybe after you're done with these questions. Sure. Before we move to the next section. Sure. I realize something I said might be misleading. I should clarify that, yeah.
Okay, we'll come back for this first for 2.1. Anyone having any ideas? Yeah, I'll just go through it then. So, we essentially know that whatever whatever inputs we want to put into the encryption function, they have to be matching. So this M1 XOR IV plus the M1 prime XOR IV prime should be matching. Why do we know this? Because we essentially want this first side of the encryption function to be the same. Knowing this, we can just rearrange terms. So we move the M1 prime onto the other side, and we get that the IE prime is equal to M1 prime XOR M1 XOR M. Make sense? Yeah.
I think like algebraically it makes sense, but like conceptually, like when looking at like the diagram, I don't get how if you XOR, so that it does the M1 IB XOR, but if you XOR some other M1, or it's a modified to whatever that might be, I don't see how that can come out the same thing out of that encryption.
The key points for if you want the same thing to come out is just that the inputs have to be the same. So I think in terms of like how the way to think about it, the algebraic way to think about it, like the inputs from both types of inputs must be equal to each other. I think that's probably the most like the simplest way to think about it. Yeah.
Wait, so you added the additional ID on both sides to get to this last one, like isolate one prime.
Yeah, so you just you all oh, that's weird.
It does like skip a step right here.
Yeah, it does kind of skip a step. But okay, basically the idea with it is what the XORs from earlier is that anything XORed by itself will just be 0. So using this property, we can isolate the IV, which is our target, by XORing both sides with M1 prime. I think this one actually XORs both sides with IV prime, but yeah. So by in order to isolate IV prime, we just XOR both sides by M1 prime. Good. All right. I'll give you guys a couple seconds for 2.2. And we'll come back in a bit. Thumbs up if we need more time. All right, let's go over it. So the only block we can change is M1. And this is what we did before by changing the IV. But the problem with changing the others is that if we look back at the scheme, it will irreversibly change the rest of the scheme, essentially. Like through 2.1, we were able to guarantee that the output of this is equivalent to the output of M1 prime XOR IV prime when you put them through, but we can't guarantee the same kind of stuff through here. Yeah. Okay. Then we'll do 2.3. I'll give you guys a couple more minutes. you're kind of stuck, there's a couple things to think about. So first, what is the output of running the back on M? And second, can we cleverly transform that output to some part of M prime? Can I get a thumbs up if we need more time? Okay. I'll give you guys 1 more minute. All right, let's go over the question then. Actually, does anyone have any ideas? Anyone want to try their solution? All right, I'll just go over it then. Okay, so we have two options. The key is that we already know this t and t prime. So if we sub it in for any part of the message, we can essentially add on the other message and get the resulting tag. So this comes in the form of using M1 and M2, and at the end of this point, we'll have the tag T. We can XOR this tag with T and M1 prime. And when we know the rest of the message, the tag of the rest of the message will become T prime. And the same thing applies for T. That make sense? All right, and the last part of this question is 2.4. Any thumbs up if we need more time? All right, so who thinks it's yes? All right, who thinks it's no? Yeah, so the answer is no. And I'll walk through how you can do this. So our target will essentially be the tag for the message A1C. And we're going to request, we're going to start by requesting the tags for A and B. Then we're going to request the MAC for A1C, and then we're going to return the message B1 TA XOR TB XOR TC with the tag A1C. See this, we can walk through the MAC process. So we're essentially just subbing in for the equation here. The thing is, this encryption function, this will return tag B over here, which will cancel out here. And we're by step 3, we're left with the encryption of tag A XOR C. Then we can sub back in C XOR the encryption of 1 XOR E encryption A. And this is equivalent to the MAC of A, 1, C. Yeah.
Wait, so you return the tag of A back to just like how you did with the B, right? In
Sorry?
the fourth line.
In the 4th line?
Yeah, so from line 3 to 4, you return the tag of A back to how you elaborate the encryption of and now
You sub this one, you sub the tag of A back for this. Okay. Yeah, so the next part will be Diffie-Hellman then. So what is a Diffie-Hellman key exchange? Well, the goal of the Diffie-Hellman key exchange is that we want to be able to derive this shared symmetric key without giving stuff that Eve can use to derive the key by herself. So we will generate, Alice will generate her own secret key, calculate G to the A mod P, and share it with Bob. This will be public key. Bob will do the same thing. And the key to this key exchange is that just using GA and GB, you cannot calculate the shared key GA to the B. However, Alice can still calculate G of B to the A, which is equal to GAB, and Bob can still calculate the same thing. So for its legitimacy, we're essentially backed by the discrete log problem. We're given G, a very, very large prime, and G to the A mod P for a random A. It's computationally hard to find the A. This is just 70 or yeah. The other thing is ephemeral, where A, B, and the shared key are discarded when done. We don't reuse them for different communications. And the last thing is forward secrecy. So even if a future secret is stolen, old messages cannot be decrypted because A and B and the shared secret K were never reported. Any questions so far? Okay. So now for public key cryptography. So the idea here is that we want to be able to share messages between two people where they don't already share a secret key. This is pretty similar to Diffie-Hellman, where every individual has two keys. This public key is known to everybody, and a private key corresponds to the public key. We no longer need to assume Alice and Bob share a key, and this function is much slower than symmetric key cryptography because it relies on number theory calculations. So for Elgamal, it's just Diffie-Hellman, but with simultaneous encrypts. So Bob has the private key B and publishes public key B is equal to the G to the power of B mod B. Alice picks a random R and computes G to the R mod P. Then Alice sends two messages. The first one is just R. The second one is M times B to the R mod P. And Bob can use this information to decrypt using his private key and get back the message. So for our say, we're picking two random large primes P and Q, and we're computing N, which is equal to P times Q. And we're going to choose an E such that it's relatively prime to P minus 1, Q minus 1, and it's greater than 2. it's between 2 and p minus 1 times q minus 1. We're going to compute decryption, the decryption key, which is the inverse of E, using the extended Euclidean algorithm. And we're going to have a public key, which is N and E, and we're going to have a private key. This is all just sounding for G, by the way. So for the encryption process, Alice has a message and has access to Bob's public keys N and E, and Bob has a corresponding private key. Alice will encrypt the message by taking the message to the power of E mod N and send it over to the insecure channel. Bob will receive the ciphertext, and because E is the inverse of D, when you compute C to the D mod N, it's essentially M to the power of E times D, which is equal to M to the power M mod N. And so Bob can recover the original message. Questions? Yeah.
About Pokemon, what benefit does it offer over distributed video? What is simultaneous?
I don't remember off the top of my head.
Okay, okay, so think of Algamal as just, let's say you publish your public key, so your G to the is known to everyone, but I'm sending a message to you. You don't know who the message is coming from. In Diffie-Hellman, you have to sit together. We both have to be online to do. In this case, she's online, I'm not. She doesn't know my R because she doesn't even know if I'm communicating with her. So you just pick a public key just at random, which is just G to the R. Same thing that you would do in Diffie-Hellman, but you would do it online. Here you do it, just you pick a random thing. You said that because the other party doesn't know that thing, but this is the shared secret that you get in Diffie-Hellman. And this thing is unknown to the adversary. So you multiply your message with that, and that hides your message. So all this is doing is, if you were to do Diffie-Hellman, when one party is not known to the other, like you don't know who the other party is, then this is pretty much the only way you can do Diffie-Hellman. And what you're doing is you're just multiplying your message to the secret that is formed in the end, because that is the only thing that is unknown to an eavesdropper in Diffie-Hellman. That is pretty much what it is.
You explain the last one again when the Bob tries to retrieve the message with when multiplying with C1 inverse.
Yeah, so C1 is going to be R, which Alice computed here, which is G to the R mod P. So Bob is going to multiply C2 times C1 times negative to the power of negative B. Now this simplifies to, since C2 is equal to M times B to the R, and this will become M times B to the R times R to negative B. Now this simplifies to, since B is equal to G to the B, B to the R is G to the BR. And since R is equal to the G to the R to the negative B is equal to G to the negative BR. And you're multiplying these two together, and the exponents will cancel out, and you'll just get M as the leftover.
And that's the original message, or
Yeah, M is the original message. Okay. I think the next thing was a question. Yes. All right, so just like last time, I'll give you a couple minutes to think about it, and then we'll reconvene. Thumbs up if we need more time. Okay, I'll go over the first one then. So can Mallory learn the value of M? Raise your hand if you think it's yes. Okay, how about no? Okay, yeah. So Mallory cannot learn the value of M, but she can change it to any value for choosing. Why is this true? Because this function up here, the encryption of P to the K of PK of bank and M is not private. Like this function or this key right here, this public key is posted by the bank, which means that anyone can literally just take this public key, any messages they're choosing, and just calculate this thing. And they can send it and claim that it's the original message that Alice sent. All right, so what about this one? Actually, this is in the way. Okay. Yeah. Thumbs up if we need more time. Okay. So who thinks Mallory can learn the value of M? Do you want to explain why?
Well, I said, well, I think it's like the hash makes it deterministic, so you just like run through messages until you get that.
Well, remember though that kind of leaked the answers. That's okay. Remember that there are too many possible values of M for Mallory to try them all. So that's the first thing, and then remember that hashes are also like one way, which means that given the hash, it's hard to recover the original message. So Mallory still can't learn the value of M, but can Mallory change the message without being detected? I'm seeing a couple of yeses. Can we say why? Sure.
Hashing doesn't do anything to protect the integrity.
Yeah. So basically anyone can compute the hash, right? Just like this function over here, the public key is public, so anyone can compute this. Anyone can also compute this because the hash function is public. All right, so next question. I'll give you another couple minutes for this one. Thumbs up if you need more time.
Thank you.
Yeah. All right, I'll go over this one then. Can Mallory learn the value of m? Anyone who thinks it's yes. What about no? Okay. Well, the answer is yes. And the reason this is true is because RSA signatures are vulnerable to the recovery of the original message. By raising s to the e power, the e and d will cancel out in the mod n space, leaving Mallory with with n mod n. Yeah.
What does that mean? Oh, sorry.
Oh,
What does
sure.
it mean like E and D will cancel out?
So we know that E and D are inverses of each other in mod space, right? So we know that, sorry, let me go back to this. Is it here? Yeah, so. Hang on. Yeah, okay, so basically, the reason we're able to do this is because E is public, right? And so what we're doing when we're signing is we're raising n to the d power. So since E is public, we can just raise the ciphertext to the e power, and that'll give us n to the de, which cancels out. And it just leaves us with the message. More questions? Okay. All right, next question, can Mallory change n without being detected? What do we think for this one? Do you guys need more time? Okay, fair enough. Yeah, any ideas? Yeah.
Is it yes, but to something that, will like have the same value of n mod p?
You're saying it's the second option?
Yeah.
Yeah. Why do you think that?
Like that, since the Mallory now knows like D, or now knows like D and E both, she can just find something that will like give the same answer in the verify the SE.
Yeah. Yeah, I think that's makes sense. So the key here is that Mallory can fix some s prime, and then use that s from that s prime. She can raise it to the e power to obtain m prime. And then since this encryption function here is public, Mallory can just compute the same thing and pass it off as the original message. Yeah, so that's right. All right, and then the next part. So I'll give you another couple minutes. Question. Oh, yeah.
Sorry, I'm still kind of confused about the previous one.
Uh-huh.
By like Mallory can fix some S prime, like what does that have to do with like whether or not she chooses it?
Yeah, so basically the way Mallory is messing with message is she fixes on S prime and she computes the message that it would translate to by raising it to the E power.
Oh.
So now that she has the M prime, not necessarily of her choosing because she had to determine it through the S, right? The signature. And then she can just use the encryption function to send the corresponding text.
Okay, wait, so could you be like when she actually like places the M prime, like where is that?
Yeah, so Mallory can't pick the M because she doesn't know the secret key deed.
Right.
But she can pick some S, and since she knows the public E key, right? She can raise S to the E power, which will give some M prime. Why do we know this is true? Because the signing method has you just raise the message to the D power, and to decrypt it, you just raise it to the E power. So if you have some signature, you raise it to the E power, it'll give you some M prime.
And why can't Mallory just assign an S prime of choose?
She can. She chooses an S prime, but that doesn't mean she can choose the corresponding message.
Oh, I see. So it's like Mallory can choose anything, it's just that what it results in is like she doesn't necessarily know.
She can choose any signature she wants. Yeah. Uh-huh. Thumbs up if we need more time. Okay. So what do we think? Do we think that yes, Mallory can learn the value of M? What about no? Yeah, okay. And why do we think this?
I mean, Mallory doesn't have the key to decrypt, so I'm just guessing that she can't.
Yeah, so essentially the difference here is that like instead of signing the message itself, she's signing the ciphertext. And so now decrypting or verifying the signature will not get you any. Yeah. And what about 3.8? Can Mallory change M without being detected?
Is it the same reasoning as before and say that you can decrypt M but with specific values?
Okay, why do you think that?
Because I think when you when you decrypt, when you need to get the original message, you need to raise to the power, right?
Yeah.
E to get the original message, right? Same as.
Yeah, so the same process will work as before, where like instead of this time, instead of deriving the message through your signing process, you're deriving the ciphertext through your signing process. So you start with some S of your choosing, you raise it to the E power, and then that will give you your ciphertext, and then you send this ciphertext and your S of your choosing. Make sense?
But also, in this case, when you change the S, because of this ciphertext, you're unable to learn like the original message.
Yeah.
Okay.
So the reason it works last time is because we were signing the message with the signing key. And so when you want to verify, you would raise S to the E power, but that would give you the original message. Any other questions? Okay, I think, yeah, that was the last question. So you guys have any general questions, concerns, etc. about the midterm? If not, you're free to go. These slides are on the inside, so if you want to review them as well.